Hi, we're Sophia, and Amelia. Our team is investigating radiation shielding for space travel. We will investigate how different spacecraft materials protect astronauts from space radiation using multiphysics simulation and COMSOL, focusing on both charged particles and secondary neutrons.
Space may seem quiet and empty, but for astronauts, it is an extremely dangerous environment. One of the most serious risks is radiation exposure. Outside of Earth's protective magnetic field, astronauts are exposed to high energy cosmic radiation, which has been shown to increase the risk of cancer and damage to the brain as well as cardiovascular system. Measurement from missions traveling towards Mars confirm that these radiation levels are high enough to pose significant health risks during long duration spaceflight. In addition to radiation, astronauts also face physiological and operational challenges such as vision problem, cardiovascular strain, and limited access to medical care during mission. There are also important psychological risks, including isolation stress and reduced cognitive performance when crews are away from Earth for a long time. As space agencies plan missions to the Moon and Mars, these risks become a critical challenge. Our motivation is to better understand and reduce these risks by developing solutions that improve astronaut safety and make long duration spaceflight exploration possible.
Use COMSOL Multiphysics as a simulation platform to study how radiation interacts with spacesuit shielding materials. The general workflow was to define radiation sources, select relevant materials, and build a simplified two-dimensional cross-section of a spacesuit shielding system. From there, we applied different physics interfaces to model particle transport and energy transfer, and then coupled them together so we could capture how radiation affects both particle motion and thermal response inside the structure. The overall approach was multiphysics in nature. First, we defined incoming radiation sources, including both charged particles and secondary neutrons. Then, we built a 2D geometry representing layered spacesuit shielding. After that, we applied particle tracing physics to model how radiation travels through materials and heat transfer physics to capture how deposited energy leads to temperature rise. Finally, we coupled the physics so that the particle energy loss directly contributes to heating in the solid layers.
The geometry is a simplified two-dimensional cross-section of an astronaut suit and surrounding space or interiors. We model the system as multiple stacked material layers, each representing different structural or protective components. Material choices are based on known aerospace systems used by NASA and the ESA, particularly polymer based fabrics and structural composites commonly used in spacesuit design. This lets us approximate a realistic shielding stack without needing a full 3D suit model. In this section, we model incoming space radiation using charged protons. We use COMSOL's charged particle tracing interface, where each proton follows Newton's second law under material-dependent forces that approximate energy loss and scattering inside the shielding layers. We released 1,000 protons from an inlet boundary with a defined initial velocity to represent the incident cosmic radiation. As particles move through each layer, they gradually lose energy depending on the material properties, which determines how far they penetrate into the material. When a proton reaches a boundary, we use a freeze condition to stop it. This allows us to determine whether it was stopped by the shielding or if it reached the interior. A particle counter then records the number of protons that successfully passed through, which is used as our main metric for shielding effectiveness. The heat transfer model is used to evaluate the thermal response of the shielding system. We solve the standard heat equation with material-dependent thermal conductivity, density, and heat capacity. The outer boundary radiates heat to space using a surface-to-ambient radiation condition, while the interior boundary is fixed at a human body temperature of 293 Kelvin. To connect particle physics to thermal effects, we introduce an energy deposition term that converts proton energy loss into heat generation inside of the material. This allows us to directly link radiation transport with temperature rise inside of the suit.
Neutrons are treated as secondary particles generated when protons interact with nuclei in the shielding materials. They are modeled using particle tracing with zero charge and the same Newtonian motion framework. We release 30 neutrons at a high energy with velocity of 80,000 meters per second to represent energetic secondary radiation. Similar to protons, we apply material dependent drag forces and freeze particles when they reach boundaries. A particle counter tracks how many neutrons penetrate through the interior region. Okay, bro, okay. We will now go over the study performed in COMSOL. The protons lose energy as they travel through shielding materials. The color gradient from red to blue represents energy decay, following ionization loss described by the beta block relationship. We also observe a Bragg peak, where protons abruptly stop, indicating that their energy has been fully absorbed by the material. Comparing materials, polyethylene stops protons within about zero point 0.2 centimeters, while aluminum requires roughly 1.2 centimeters to achieve the same level of protection. This highlights that polyethylene is significantly more efficient, as its high hydrogen content allows for similar shielding with reduced thickness and overall mass.
The heat transfer results show that peak temperature occurs in the middle shielding layers, particularly in polymer-based materials like polyethylene and polyurethane. Outer layers remain relatively cool due to exposure to vacuum and radiative cooling. We also observe sharp temperature gradients at material interfaces, which indicate localized energy deposition from incoming radiation. For the neutron model, we evaluate the number of particles that reach the detector region under different material configurations. A parametric sweep over material thickness shows clear separation in shielding performance. Polyethylene provides the strongest shielding, followed by polyurethane, Kevlar 49, aluminum, and finally nylon, which shows the weakest attenuation. This leads to an important design trade-off. Aluminum is effective at stopping high-energy protons because it has high density and strong interaction with charged particles. However, it also contributes to secondary neutron production when struck by cosmic radiation. In contrast, hydrogen-rich polymers like polyethylene and polyurethane are far more effective at moderating neutrons because hydrogen atoms efficiently slow them down through elastic scattering. So, polymers are superior for neutron shielding, while aluminum is stronger for proton shielding. In the context of astronaut protection beyond Earth's magnetosphere, no single material is sufficient on its own. Our results suggest a layered shielding strategy. A thin outer aluminum layer provides structural integrity and proton shielding. In terms of mass efficiency, polyethylene is actually a more effective material at proton shielding. However, per area, metals like aluminum are still more effective. This is followed by thicker hydrogen-rich polymer layers that are highly effective at absorbing and slowing secondary neutrons. Finally, a thin inner structural layer helps distribute thermal loads and maintain mechanical stability. Overall, the optimal design is a hybrid system that balances structural requirements, thermal management, and radiation protection simultaneously. Thank you for watching.